Welcome back again to Physics Galaxy, and today we're going to solve some quantum mechanics problems which were asked in last CSIR NET examination. Alright, so the first problem is a system consists of two non-interacting identical spin half particles. The spatial wave functions for the individual particles are given by phi1 of x and phi2 of x. Let x1 and x2 denote the positions of the particles respectively. The total wave function of the system, not necessarily normalized, can be. Okay, so these are our possible wave functions, okay, of two identical spin half particles. Okay, so as we know, so these are two non-interacting spin half particles. So spin half particles. So spin half particles means they are fermions, right? So they are fermions. And fermions obey Fermi-Dirac statistics. Fermions, right? Now, for fermions, what we know is that the wave function, suppose let me denote that by capital Psi, has to be antisymmetric. So this has to be antisymmetric. Antisymmetric. Okay. So that means, okay, so psi has to be antisymmetric for fermions. That we know. Okay. But because these are spin particles, the psi will be combination of the spatial wave function and the spinor component. So it will have both, okay, phi and spinor part. Okay, so that means we can rewrite the total wave function as, now spinor will have two parts, so it will be, let me write it. So particle 1 in at position x1, particle 2 at position 2. अब प्लस माइनस that will decide later on क्या होगा. Particle 1 at position x2, particle sorry, wave function particle 2 at position x1. So this will be the complete spatial wave function. Okay, now what about chi spinor part? So let me write that down with this red. Okay, so chi will be multiplied by particle 1 in the up state, okay, and particle 2 in the down state, okay, spin down, plus or minus, so that will decide later on क्या आएगा. Particle 1 in down state and particle 2 in up state. So these are the possible combinations, right? Now total wave function has to be antisymmetric, so that means it has to be minus. So plus is for bosons, plus is for bosons, and minus is for fermions, right? Fermions. So अब देखेंगे कि क्या हो सकता है. So this अगर अगर ये वाला प्लस होगा, so that means this has to be minus, so that overall plus minus will give us minus. Both अगर माइनस माइनस होंगे तो that is not possible. अगर ये माइनस होगा, अगर स्पेशल का पार्ट माइनस होगा but supinor part plus होगा, that is also possible. Okay, so let's check options directly. So see, if we look at the first option, the special part is minus. Okay, here it's antisymmetric. Okay, this is antisymmetric, and the spinor part is symmetric. So antisymmetric and symmetric gives us antisymmetric wave function. So overall it's antisymmetric. So this is the option. Okay, that's correct. Now let's look at other options as well. So the spatial wave part is symmetric, that means plus, but the spinor part is symmetrical again, so that means plus. So this is symmetric. Okay, so this is not an answer because the total wave function has to be antisymmetric. Okay, now the third option, this is symmetric, this is symmetric, again plus plus plus, so not an option. This one, spatial part for the fourth option is antisymmetric, and the spinor part is again antisymmetric, and minus minus will give us plus. So the only option is the first option, that is the correct one. The next question is, again from the spin half system. A spin one half system is prepared in the initial state phi, which is given as root 3 by 2 spin up. Let's call it spin up plus 1 by 2 spin down, where spin up and spin down are the eigenstates of Sz with eigenvalues plus h cut by 2 and minus h cut by 2 respectively. A measurement of Sz is followed by a measurement of Sx on the system. What is the probability that that measurement of Sx yields a value of plus h cut by 2? So two measurements are done simultaneously. So suppose this is our system. Let's so okay. So this is a box which is our system. Suppose okay, where we have spinners, and then what we do a z measurement, that is a spin along the z direction, and then followed by sx, that is a spin measurement of spin along the x direction, and what find what's the probability that will get plus h cut by 2. Okay, okay, so this is our initial state phi. So this is our initial state phi, which equals to root 3 by 2 spin up plus 1 by 2 spin down. So when we'll do LZ measurement on this state, so we'll have two possibility. Either we'll have spin up or we'll go spin down. Okay, and this will have spin up will have the probability of the square, that is its probability will be 3 by 4, and spin down will have probability of this square, so that is 1 by 4. Then followed by this, so this was SZ measurement. So this was SZ measurement. So SZ. Now again, what we'll do SX measurement. SX measurement. So if we do SX measurement on this, so we'll have again two possibility. So for this again two possibility, right? So here we'll have two possibility, that is 1 by root 2, because it will lost SX measurement will lose the information what was previously. Okay, so it will give us position of up plus down. Okay, let me write it in a more compact way. So we'll have 1 by root 2 up plus down. So I'm not writing those brackets. Or we'll have 1 by root 2 up minus down. Similarly, in this case, we'll have 1 by root 2 up plus down, or 1 by root 2 up minus down. Okay. Now probability of this will be half, probability of this will be half, so they will be equally probable. So similarly half for this and half for this. Now what is the probability that we'll get sx equals to h cut by 2? So that means either this one or this one. Okay, so that means probability from this to this will be 3 by 4, then probability from this to this will be 1 by 2. So the total probability from this to this will be 3 by 4, 3 by 4 times 1 by 2. So this is for path 1. So this is path 1. So this is path 1. Okay. But we can also have this pro kind of path. So it will have plus 1 by 4 times 1 by 2. So that equals to 3 by 8 plus 1 by 8. That equals to 1 by 2. So 1 by 2 is the answer. Next question is, the energy eigenstates of a one-dimensional harmonic oscillator are denoted by I, while I equals to 0, 1, 2, 3, so on and so forth. If the momentum operator P satisfies this given condition, then the value of n is okay. So we have this condition, n plus 1 P acting on n divided by 2 P1 equals to root 2. Right, and P we know momentum operator, we can write it as iota under root h cut m omega by 2 a plus, that is the raising operator, minus a minus, that's the lowering operator. Right, so let's see calculate plus the numerator part, so that is n plus 1, and then we'll have iota h under root of h cut m omega by 2 a plus minus a minus, then we have n. Okay, so we can take this constant part out, so that is under root of h cut m omega by 2, then we'll have n plus 1 a plus minus a minus n, right? So this will act on first this, then we have this. Okay, so we'll get two uh, terms here. So one will be n plus 1 a plus n, then we'll have minus n plus 1 a minus n. Now we know when a plus acts on n, so it will give us under root of n plus 1, n plus 1. Okay, and when a minus acts on n, it will give us root n, n minus 1. So here we'll have n plus 1 root n plus 1 n plus 1 minus n plus 1 root n, and then n minus 1. Okay, now root of n plus 1, this is a constant, so root of n plus 1, and then we'll have n plus 1 n plus 1, so that will be equals to 1 simply. So 1 minus, so this is n plus 1, this is n minus 1 state, so their inner product will be 0, so simply it's under root of n plus 1. Okay, so the numerator part we have is, it's simply iota h cut m omega by 2, then we have root n plus 1, root n plus 1 divided by, so in the denominator we have 2p1, so we can say it n plus 1 equals to 2 and n equals to 1, right? So that means we'll get iota under root h cut m omega by 2, and simply we'll have under root of 2, okay, and so that's given as equals to root 2, so this and this cancels out, so what we're left with, so it went n, so it implies root n plus 1 equals to 2, implies n plus 1 equals to 4, or n equals to 3. So that's your answer. The next question is, a particle of mass m is in the third energy eigenstate of an infinite potential well of width a. The time interval in which the phase of this wave changes by 2 pi. Okay, so particle is in an infinite potential well. Okay, so this is our infinite potential well of width a. So this is width a. Okay, the wave function changes by 2 pi. So wave function we know is given as, so we can write it like this. So it has psi of r, and t can be written as psi of r e to the power minus iota e t by h cut. Okay, now the phase changes by 2 pi, so that means this is the phase part, so that means it changes by 2 pi, so that means e delta t by h cut will be equals to 2 pi, right? So we have to find the time interval, so delta t will be equals to 2 pi h cut by e, right? So now energy in the third state, so E3, so we'll have 2 pi h cut, so it's equals to n square pi square h square by 2m a square, so that is the energy of the third state. So we'll have pi cancels out, pi, and we'll have so n equals to 3, so it will be 9, so we'll have 4m h cancels out, 4m a square by 9 I h cut. So this will be the answer. So which is 4m a square 9 pi h. So that is option number 2.